This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
And we now have Kevin Shen, who is going to talk about classification of the Fashion-MNIST Dataset on quantum computer.
Hello. Yeah. So I'm going to talk about the topic classification of the Fashion-MNIST Dataset on a quantum computer. This work is done together with my collaborators, Bernard and Frank from Technical University of Munich, and Elvira, who is in BMW. So this project was done when I was still doing my master's at TUM, but now I'm affiliated with Leiden University and BMW Group for my PhD. How can I switch slides? Just click forward. Sorry. Yeah, it works. Yeah, so I hope this talk will be interesting, particularly for people who are interested in experiments and applications, so I will keep my language simple, but to compensate for the theorists, I will also include a related work by the same people about theory. Yeah. So first of all, what is data encoding? Data encoding is about loading classical data that were stored on your classical computer into quantum states. And why do we care about it? When do we need it? We need it when we want to process the classical data by some quantum algorithms. And many quantum algorithms can be divided into two parts, data encoding plus data processing. And when do we not need data encoding? There are many cases. First, if our data is just given as quantum states, and second, if we are having some generative modeling algorithms where we only output data but not input data. But for this talk, let's assume that we are in the first case, that we actually need to do data encoding. So now consider some high-dimensional real data. How do we do data encoding? Well, there's a decision to be made. Do we look for quantum advantage from encoding or processing part of our algorithm? If we assume it comes from encoding, then you can go for quantum feature maps. Basically, the intuition is you map your data into some high-dimensional hyperspace. You can think in a picture of kernel methods or variational circuits. They are basically the same with a little difference. You can check the references. If we assume that our quantum advantage will actually come from the processing part, then what you need is an encoding scheme that is resource efficient and keeps sufficient information that you need for the processing. And there are many methods that you can encode the data. One of the examples is amplitude encoding. It is arguably the most common encoding method in quantum algorithm literature. Is it efficient? Unfortunately, no. If you count the number of gates that you need to prepare amplitude encoding, it's exponential in the number of qubits. So what are the consequences? Well, it just makes quantum advantage from processing more difficult, right? If you have an exponential disadvantage in the beginning, then you won't have any advantage in total. And second, it's also challenging for you to experimentally realize your algorithms and observe the behaviors. So what can we do? Our motivation is to make amplitude encoding more practical for quantum machine learning experiments. We can choose to do data compression. By compression, I mean some efficient but approximate encoding. And this would be useful if your processing algorithm is actually robust against noises in data. And fortunately, in machine learning, it's usually the case. Sometimes noise can even help as a regularizer. And how do we evaluate the performance of a data compression routine? There are many ways. First, we can check the fidelity between the prepared state and our target state, which is the exact amplitude encoding, or we can look into the performance of the processing task using the compressed states. So how exactly can we do data compression? Well, if you look at the literature, most of them will go for matrix product states. What is matrix product states? It is one way to classically store a 1D quantum state. But you can also think of like general classical data. And amplitude encoding of data actually goes to the class of 1D quantum states. In matrix product states, there is one degree of freedom that you can do. It's called bond dimension. Basically, if your bond dimension is large enough, you can exactly represent the state. And if you lower the bond dimension, you can get rid of the less important information and compress the data. And the general rule is if your state has low entanglement, then you can approximate it with a low bond dimension, and it gives a low approximation error. And how can we use matrix product states as a part of the workflow doing quantum machine learning? We can classically optimize matrix product states, tune in the bond dimension to, for example, keep it above a threshold in terms of fidelity. And then we write the matrix product states in the so-called right canonical form, and then it can be mapped exactly to a sequential shaped quantum circuit, shown here bottom right. And you can count the number of gates needed for this circuit. It scales basically square in the bond dimension, and it's logarithmic in the dimension of your data. And this is like significantly smaller than exact amplitude encoding, which is linear in the dimension of the data. And one key question is, of course, how big is chi in practice? It better not be like O of n, otherwise you won't have any advantage. So our first research question from the rather theoretical work was how, why can we assume that we have a low bond dimension? We checked that in amplitude encoding and in a related encoding method called flexible representation of quantum images, when you apply them to real-life images, they typically have low entanglement, and this gives, of course, low bond dimension. So if you look at the blue line and the orange one, they are for amplitude encoding and FRQI encoding. You get like a small entanglement entropy, irrelevant of the resolution of the image. And why do we consider FRQI? I didn't introduce before, but it's an alternative way to represent images. It has the benefits over amplitude encoding because it preserves the global color scaling. So imagine you have two images, one completely white and one completely black. In amplitude encoding, they look exactly the same because you normalize the pixel values, but in FRQI, it's actually preserved. To make it more concrete, you can see some example images. Like on the left, it's exact encoding, and on the right is when you compress it by bond dimension 64. Going beyond that, we actually derived an error bond. We proved that regardless of image resolution, you can use an MPS using bond dimension of about this scaling, and it guarantees an epsilon approximation error in terms of infidelity if your data has algebraically decaying Fourier coefficients, and this is satisfied by most natural images we checked numerically. And there's like one remaining question: how do we compute the MPS in practice? Well, you don't have to worry because like there's a lot of literature on this. You can do SVD, that's the simplest case. But in other cases, you can use stochastic methods or interpolation methods, and they are like more efficient and still accurate in most cases. And the second question is, can we make it even more experiment friendly? Let's say you want to run some experiments on today's machines. So here, again, it's the exact MPS circuit. We can replace it by, variational circuits using like repeated layers of sequential ansatz. And we can also further reduce it by even sparser circuits, considering native gates of some hardware. And we want to observe the trade-off between efficiency and accuracy in experiments, meaning that we want to see, like in sparser circuits, although like the expressivity is smaller, like you get larger approximation error, but since it's simpler, you get accumulated fewer hardware errors, and overall you can witness the performance of your algorithm better. So we tested on a variational classifier. We compressed the full data set of Fashion-MNIST and simulated the training of a 10-class classifier on a classical computer and then deployed it on a IBM device, which is not available anymore. So this is basically the results. Like the red curves are the results from the simpler ansatz, and the blue curves are from the denser ansatz. So although like on simulator, general circuits, like more dense circuits perform better, but on real hardware, like the simpler ansatz perform better. So finally, what can we do together? I would suggest like we can think more about the data encoding problem, although like we don't usually talk about it, but it's really important if we want to observe empirical quantum advantage through experiments in the near future, maybe on NISQ devices, maybe on early fault tolerant devices. But if you want to do it, like just think about it. Yeah, so I will stop here. Thanks.
Thank you very much. Do you have questions? I see a couple there.
It's me again. Hello. Right here.
Oh, hi.
What was the first of all? It's two questions. What was first one? What was the x-axis in the plot that you showed? I don't think there was a label.
Oh, so on the x-axis, it's the gate count, basically, like the number of gates you use in the circuits.
Okay. And what are the numbers there? Do you know?
Well, you can check the paper. Sorry, I cut it off.
Okay. Another question. I think in the beginning you said that the amplitude encoding is exponential in the number of qubits, the gate count.
Yeah.
And then afterwards you said that it's linear in the number of parameters.
It's exponential in the number of qubits, but linear in the data dimension.
But that's only if you use the entire binary basis.
Sorry.
I agree that it's linear in the number of data points that you have. Only exponential number of qubits if you use the entire binary basis. For example, Snehal mentioned the unary encoding before lunch. And there you don't use the entire binary basis, so it's not exponential the number of qubits. You have an exponential number of qubits, but then you don't have an exponential number of gates. But there is also the Hamming weight, fixed Hamming weight encoders, where you use instead of doing full exponential compression in the space, you do polynomial compression, and then it's a trade-off between unary and binary, which are the limiting cases. So my point is that linear in the data is not always exponential number of qubits. It depends on the encoder that you use. Just a point to raise.
Okay, I think it's quite technical. Maybe we can discuss later. Yeah.
Okay, maybe we can take another question while the last speaker is setting up.
Hi, great talk. When you talk about it being like chi squared log n, is that before or after, like once you've done the decomposition into 1 and 2 qubit gates, it's still exponential in the number of gates you need for an arbitrary sort of given state vector, right?
No, it's not exponentially many gates. So chi is not, chi is typically just a small constant.
Sorry, maybe we can talk about it later. It might take a bit too long.
Okay, let's thank our speaker again.